Hi, I'm Yesh Devabhaktuni. I'm going to be presenting the chess movement validation paper that was written by Shan Siraj in 2017. So let's get started. The agenda for today is a basic introduction and the motivation for an approach uh, to solve this problem of recording chess games. The techniques and processes that were used to validate, detect, and update chess games, um, which we're gonna look into in a lot of detail, and a conclusion of this play to this paper. This is the general setup of this particular paper. So initially, the image capturing from the camera happens, and the camera takes a particular picture, sends it to the program, and the first thing that happens is rotation detection, which we'll talk about right in the next section. Then there's the corner detection in each of the squares in the chessboard, the empty chessboard. There's no pieces in it. Next, the piece detection and the general square detection from the aerial view. The next thing in the process is the arrangement detection from different sides of the players, and then validating all of this detection from of the arrangement from the sides of the players. After that, we do the chess piece movement detection. Initially, it's the motion detection that's done after one of the players changes the location of a particular piece on the board. Then there's movement validation, which is making sure that the move itself was valid as compared to the most recent snapshot of the screen. The next thing is we're just going to send the most recent snapshot to be verified to a virtual judge, and it's going to be sent to a server and verified on the server as well. Okay, so here I'm going to be discussing a little more about the techniques and processes that are being used. So the first step in this entire process is rotation detection. So, for example, if the board is not, or the image of the board is not perpendicular to the camera itself, or the camera is not facing right, staring right down at the board itself, we detect each of the squares and we calculate an angle between the square and the camera direction. And right here, we get the inverse tan of that particular angle, and we rotate the square in the program by that particular angle. So in this particular detection, there's a detection of these particular regions. This happens by detecting the black and white corners in such a way that if there's a white corner before and after a black corner, then that is one of the points. And if there's a black corner before and after white corner, then it's a black corner. I'm sorry, I meant black pixel before and after a white pixel. Then that's considered a white corner. And then if it's a white pixel before and after a black pixel, then it's considered a black corner. So the next step in the process is trying to detect each of the squares. Um, the board is scanned from the left to right and top to bottom in this process, and zeros are set for white boxes and ones are set for black boxes. If there's a huge concentration of white pixels or low intensity pixels concentrated around a certain area, that's considered a white box. If there are a lot of black pixels concentrated around a certain area, that's considered a black box, and that's done to the entire image to validate it and to make sure that there are a total of 64 squares and the white and black squares are divided 50-50. Um, the next step in the process is detecting the borders. Any sudden change in intensity can detect the change from white to black uh, pixels, or high intensity to low intensity pixels. So essentially, when this happens, um, the line along that border is detected, and an intersection of those borders generally gives these points, the corners, and that's essentially the point of this particular section. So the next idea the paper explores is the initial arrangement validation from the top view, which is like the aerial view. Um, a picture or a video of the chess setup initially is taken from the top view and it's fed into the program. And essentially, what this program does is, as you can see here, uh, greater than 99.9% percent average number of black pixels indicates an empty black square. Same goes for the white square. For example, um, white pieces on a black square are relatively easy to find or understand because um, the number of gray pixels is between 15 to 100%, which implies a white pixel in a black square, and the rest of them are were pretty easy to detect because there were certain number of or percentage of pixels that did not match the rest of the pixels intensities in the square itself, and based on this, it, we were able the paper was able to determine that there were pieces on the square itself. Black pieces on black pixels were the hardest to detect. So the light source was probably the most important scenario. The light source generally plays a very important role in this particular paper. And when the light source was directly falling on some of these black pieces, um, the intensity or the shine was greater on some of these black pieces. So that was the one thing that made it easier for black pieces to be detected on black pixels. Shadows also caused a bunch of problems. So if you look at the figure 5 on the right, um, there's an internal margin that's created, and pixels are only extracted from that internal margin to determine whether there's a piece in the middle or not. And the rest of the pixels outside the margin are mostly averaged out to make sure that the intensities are different from one another. And this way, it was detected whether there was an actual piece in that particular square or not. The next step in the process is just a matrix representation of each of the squares and their validations. The W stand for white and the B stand for black, which are on either sides of the chessboard. And it's a 7 by 7 matrix that's being used in order to store information about the valid setup of this particular chessboard. This is just more of a parallel matrix that will be used throughout the course of the detection part of the process, which will probably be more clear in the next couple of sections. The next step in the process is to detect each of the pieces in the rare side from the player's sides of the board. So, as you can see, the image on the left is kind of what I'm talking about. There's the king right here who has the highest x value. I'm sorry, highest y value, and detecting the x values as you scan from the left to the right and the top to the bottom generally gives an idea of how many pieces are in the rare. And the y values give an idea of the difference in heights of each of these pieces. Zeros are assigned to each of the black pieces that are detected, and ones are assigned to the to the intensities in between them. That's how each of the pieces are detected. Once they're detected, they're essentially validated to make sure that the right pieces are present in the rare. Um, each of these two images essentially show the same idea that I tried to describe here. In figure 8, you detect the width of each of the pieces by detecting the starting x value and the ending x value, subtracting them from one another, and getting the average to get the line in the middle. That shows that it is a piece that is detected. And on the right, you can see the difference in the height. This gives the height of the piece and makes sure that it's lesser or greater than some of the other pieces. After all of this is done, each of the heights are measured, and it's made sure that um, all the pieces in the rear flank are present. Now, this picture shows the arrangement validation from the view between the players. This is essentially useful to detect mainly just the pawn. Um, on the left side is the king and the rest of the other pieces that are on the rear, but we know and have detected all the pieces in the rear and validated them. The next step in the process is to make sure that there are pieces to the right of the king that are much shorter than the king. The pawn comes in the height of the pawn comes in at approximately 40% of the height of the king. When we take the difference between the y values at the top here and the bottom here, this way we can make sure that there are no differences in height between any of the pieces here, and that way we've validated that in front of there are pawns in front of the rear flank. And as far as making sure that all the pawns exist go, it was already done in the aerial view that was discussed a couple of sections ago. Once all the validation of each of the pieces and the entire chessboard is done, the matrix that was described a couple of sections ago is updated to contain some of the algebraic notations shown on the right. So K for king, Q for queen, N, B, R, and P for pawn, and that's what is filled up right here. Along with this, in the program, there's also an identifier to check that these are white pieces and these are black pieces, but that's just not shown here. And each of the moves from one location to the other is receives algebraic notation, which I'm going to talk about in the next couple of sections as well. Now, the next part of the process is motion detection. What I mean by motion detection is not the movement of the pieces itself, but every time a user moves a piece from one point to the other, there's a spike in either the white color or the black color, and this spike essentially shows that there was a change from the current assembly of the chessboard to a completely new assembly. And what happens when this particular process happens is that the movement detection process is triggered. So every time this motion detection happens, it triggers the movement detection function, which essentially takes the captured image after the motion detection happens and compares it with the initial board or the initial image. So the idea behind the initial image or initial board is that it keeps getting updated every single time a change in um, the location of the pieces occurs. So what happens then is the captured image is compared with the initial board or like the most recent image, and the changes in the location of the pieces is noted. So, for example, if there's a horse that's in one location and it's a white horse, and there's the black queen that's in another location, and the black the white horse was to take out the queen, then what would happen is the location of the white horse would be in place of the location of the queen in the previous captured image. So this is detected using some of the techniques that I described before, including in the initial board detection, in which there's an internal margin and um, the external and the rest of the square that has a black or white intensity. And every time that is detected, and every time such changes are detected after every move, they're written into the parallel 2D matrix that was described in the previous sections. Um, the most important thing to note here in this particular stage is that there can only be one move, and that's what we're counting on, and that's how we're detecting the change. Um, so the next course of action is that we're noting down each of the squares from left to right and from top to bottom. Left to right is A to H, and top to bottom is 8 to 1. So the topmost and leftmost square is going to be A8, and then below that's going to be A7, A6, and so on. And this is the algebraic notation for each of the square locations. And every time a piece is in a certain location, um, the algebraic notation of that particular square is detected, and what kind of a piece is on that square is also detected. So, for example, if there's a white horse on A4, right, that particular location is detected and kept track of. The final piece of this paper, in which the recording of the chess game takes place, is that there's a communication protocol built on top of the TCP/IP protocol to transfer movements of this chess game to a server, and the server updates the client-side application in order to react to the updates in the server. Um, every time a change in um, the gameplay takes place, the client essentially just prints words saying that, for example, the queen moved from location A8 to H6, for example, and that is the reason why algebraic notations are also kept track of in the matrix, along with each of the pieces and each of the locations of the square as well. Now, there was some testing done by Shan, who was a person who wrote this paper after he implemented the entire program. And as you can see on in the first table, the rotation results were close to near perfect because the final status, as you can see, is perpendicular every time there's an angle of, say, even 10 or 32. And using his algorithm, he was able to get it to be perpendicular. And most of the time, his results were accurate. The same goes for the motion detector part of it. Before there was a hand, there was a certain number. There were a certain number of white pixels. Um, During the move of the hand, there's a certain number of white pixels. The number of black pixels actually goes down, and the number of white pixels goes up, and that's how the motion detection is essentially detected. Um, and also, given the right light conditions, there was 96% accuracy in movement detection and rollback setup. Setup is essentially when a movement occurs on the chessboard and the movement itself is invalid. Um, the program rolls back and suggests the chessboard also to roll back. Um, yeah. And in conclusion, as I stated before, light conditions play the most vital role in detection of each of the pieces, detection of each of the squares, etc. The standard heights of the pieces and of pieces detected and validated, which has not happened before. So this is probably the most important part of this paper, that all the pieces were detected in an accurate manner and making sure that they were placed in the right locations without any errors before the game starts, so that there can be no interruption during the game. And motion detection is also something that was an original idea in this paper. As soon as the motion detection occurs, there's a trigger for the movement detection as well in an automated manner. Um, and these are essentially the biggest things explored in this paper. So yeah, thank you.